The class of Lebesgue integrable functions is quite large, but nevertheless there are very simple looking functions that do not belong to this class. So we begin with an exercise. Let I be an unbounded interval, show that if c is not equal to 0, then the constant function c is not in L of I. So even constant functions need not necessarily be Lebesgue integrable if the interval is unbounded. So if you start with the Lebesgue integrable function, you can always write it as the difference of two functions u and v, where u comma v are both upper functions. This is the very definition of a Lebesgue integrable function. But u and v are limits of step functions. This is also by definition. So the net upshot is any function in L of I is a limit of step functions almost everywhere. So any Lebesgue integrable function can be expressed as a pointwise almost everywhere limit of step functions. But the converse is not true, as this exercise above will immediately tell you. But the converse is not true. The limit of step functions need not always be Lebesgue integrable. So this prompts the following definition. A function f from I to R is said to be measurable if it is almost everywhere a limit of step functions. Okay, so the collection of measurable functions on I is denoted M of I. Okay, as a trivial observation, observe that if f is a measurable function on I and j subset of I is a subinterval, then f restricted to j is measurable on j. This is just an obvious consequence of the definition. So this class of Lebesgue integrable functions are a subset of the class of measurable functions. Obviously, we would like to have a nice criteria that will guarantee that a measurable function is Lebesgue integrable. This arises in practice because many times we can exhibit functions as the limit of step functions, but the limit of step functions need not in general be Lebesgue integrable. So it would be good to have some sort of criteria. And the next simple theorem, which is actually just a trivial corollary of the dominated convergence theorem, gives us a simple criteria. Let f be in M of I, and suppose mod f is less than or equal to g almost everywhere where g is Lebesgue integrable. Then f is also Lebesgue integrable. So we have this straightforward criteria to check whether a measurable function is Lebesgue integrable. The criteria is that its absolute value must be dominated by a Lebesgue integrable function. Let's see a proof of this. It's very straightforward. So we have a sequence, let Sn be a sequence of step functions that converge almost everywhere to f. Now we know that mod f is less than or equal to g almost everywhere, and g is Lebesgue integrable. So by a corollary to the dominated convergence theorem. So if you want to know exactly which corollary this is, watch that video on the applications of the convergence theorems. By a corollary to the dominated convergence theorem, it follows that f is Lebesgue integrable. So in the original statement of the dominated convergence theorem, you require each function in the sequence to be dominated by g. In the corollary, which was an application of the dominated convergence theorem, we saw that it is enough if the limit function is dominated in absolute value by a Lebesgue integrable function. You can still apply the dominated convergence theorem. Okay, so we have this simple criteria which immediately gives us several nice corollaries. Corollary 1: if f is measurable and mod f is Lebesgue integrable, then f is Lebesgue integrable. This follows immediately by applying the previous theorem. Corollary 2: if f is measurable, bounded almost everywhere, and I is also bounded, then f is Lebesgue integrable. This is also immediate by observing that a bounded function, there is a supremum, and if you take that maximum absolute value of f, that constant will be integrable on I simply because I is a bounded interval. So we have several simple criteria for checking whether a function is measurable. Let's see yet another criteria, theorem. This theorem will tell us how we can combine measurable functions to get measurable functions. Let phi from R2 to R be a continuous function. Let f comma g from I to R be measurable. Then phi of f comma g from I to R is also measurable. In particular, f plus g, f times g, mod f, maximum of fg, and minimum of fg, these are all measurable functions. Simply by varying the choice of phi, we can get each one of these functions. Let's see a proof of this. Again, there is nothing really much to show. Let Sn converge to f almost everywhere and Tn converge to g almost everywhere. These are step functions. Because f and g are measurable, such step functions exist. Now observe that phi of Sn comma Tn obviously converges to phi of s comma t almost everywhere by continuity, and phi of Sn Tn is a step function, or rather a sequence of step functions. The fact that this is going to be a sequence of step functions can be easily derived by looking at the partition which makes Sn a step function and another partition that makes Tn a step function, and taking a common refinement and observing that on that common refinement in each subinterval the value is just given by phi of Sn Tn. So this allows us to combine measurable functions to get more measurable functions. Now finally, suppose we have a sequence of measurable functions. Then is the limit also measurable? This is an interesting question to ask, simply because a limit of Lebesgue integrable functions is not Lebesgue integrable. You can check that. So this property of being closed under pointwise limits is not enjoyed by the class of Lebesgue integrable functions. That's why we are interested in this class of measurable functions, which cannot be enlarged in any easy manner. The previous theorem sort of says that any algebraic combination of measurable functions will be measurable. The next question is, can you go outside the class of measurable functions by taking pointwise limits? Well, the next theorem will say this is not possible. Theorem: let Fn from I to R be measurable, and suppose Fn converges to F from I to R almost everywhere. Then the limit function F is measurable. Okay, proof. What we are going to do is we are going to sort of modify this function Fn to make it Lebesgue integrable. Okay, now the basic idea is that first we sort of make the function bounded by making Fn by 1 plus mod Fn. If you consider Fn by 1 plus mod Fn, this would be bounded. But a bounded function need not necessarily be Lebesgue integrable. So what we are going to do is we are going to sort of mollify this function by multiplying by a function g, where g is some function which is there in the class L of I. For instance, one function which will always be there in L of I irrespective of what I is the function 1 by 1 plus x squared. For instance, you can take g of x to be this. This function is Lebesgue integrable for any interval, which we have seen as an application of the convergence theorem, is Lebesgue integrable on any interval. It really doesn't matter. So once you consider this new function Fn of x, capital Fn of x, to be by definition g of x. So let me not call it capital Fn of x and confuse you because there is a small. So let's call it Hn of x. Hn of x is by definition g of x into Fn of x divided by 1 plus mod Fn of x. Okay. Now observe that mod Hn of x is less than or equal to g of x. Oh, of course, where g is in L of I and g is strictly positive. This is also crucial. We want a strictly positive function which is Lebesgue integrable. So mod Hn of x is less than or equal to g of x. Hn is measurable by previous theorem. Okay, and because mod Hn is less than or equal to g of x, it follows that Hn is Lebesgue integrable. Okay, now observe that if you define capital H of x or just small h of x, by definition to be f of x times g of x divided by 1 plus mod f of x. We have h and x converges to h of x almost everywhere, because fn converges to f almost everywhere. Okay, which means we have this sequence of Lebesgue integrable functions that converge to this function h, and mod h is also less than or equal to g almost everywhere. It follows that h is Lebesgue integrable by dominated convergence theorem. Okay, now because h is in because h is Lebesgue integrable, h is in M of I as well. H is measurable as well. So all this trick to mollify this function fn by multiplying by g is just to get a function that involves this f, which is measurable. Okay, so we have got that this function h is measurable. Now what we are going to do is we are going to play this algebraic trick. You look at f of x multiplied by g of x minus absolute value of mod h of x. Okay, so this is just an algebraic trick. Okay, what is this? Let's expand it out. This is going to be f of x into g of x minus mod f of x divided by 1 plus mod f of x. And if you expand this out further, you will get f of x g of x divided by 1 plus mod f of x, which is just h of x. Okay, so what we get is that f of x is nothing but h of x divided by g of x minus mod h of x. Okay, and by the previous theorem, it follows that f is in M of I. Of course, I must mention we have also used the fact, repeatedly the fact, which was not stated explicitly in the previous theorem, but I'm stating it here. We have also used repeatedly the fact that if f of x is not 0 almost everywhere and f is measurable, then 1 by f is measurable. Essentially, I stated things about product and absolute value. The reciprocals also do not take you outside the class of measurable functions. If you have a function that is not 0 almost everywhere and measurable, if you take its reciprocal, it continues to be measurable. Okay, so we have managed to show that f is a measurable function. So what is the moral of the story? Moral is it is very difficult. It is very difficult to construct a non-measurable function. In fact, recall that when we had constructed this example, or rather we had shown that it is not possible to define a measure on the whole of power set of R, we had sort of come up with this weird set which has 1 point from each equivalence class. Well, it turns out that you can use that to construct a non-measurable function. So to quantify, you can say that one needs axiom of choice to construct non-measurable functions. whatever you do in normal day-to-day mathematics, that is algebraic manipulation of functions or taking limits of functions, it is not going to take you outside of the class of measurable functions. So for all practical purposes, you can assume that any function that you encounter in practice is just a measurable function. So this class M of I is sort of like the optimal class that the analyst is interested in. This is a course on real analysis, and you have just watched the video on measurable functions.